Okay, so here in the mail, let me know if anybody didn't get it. I have the codes and the presentation. So my recommendation for you is to use for this simulation, use Jupyter. Jupyter is a notebook based on the web browser. So you can go and download it from Anaconda website. You go download it. It takes around 10 or 15 minutes to download. And once you download it, depending on your operative system, you can go here and just type Jupyter notebook, enter, and it is going to open the browser. Okay, or the other option, you can ask me later if you want to do it, but usually if you don't have access to Jupyter now, you can go and type Colab Google or Google Colab from collaboration. You go to the this link that has this infinite or this CO icon. You click on it, and it opens a new notebook. So you can go sync up. What is this? Oh, sorry. And you can start. You can have like open a new notebook here. Yes, you can go here, new notebook. And this is gonna save it in your Google Drive account. Yeah, if of course you need a Google account to use it. So here, this is kind of a Python notebook for those that have some experience. Okay, so this simulation course or these simulation talks are going to be in Python. So hopefully most of you guys have some kind of experience on coding with Python. So I think in Colab you're going to have the same or similar experience than in Jupyter. Okay, so today, they're gonna talk about the basic ways to simulate stochastic processes in systems biology. Okay, so as many of you guys know, gene expression is the way how the cells from information decoded from DNA, they produce proteins. So the DNA has a given code, and depending on the letters of the code, it produces kind of a protein, a particular protein, or different copies of the same protein. And given that the number of proteins is around thousands or tens of thousands inside the cell, people in the beginning were talking about 30 or 40 years ago, they expect that the proteins inside the cell should have a very steady or stable concentration with no many fluctuations because the number is very high. However, with the discovery in 2008 of the green protein fluorescence, green fluorescent protein, and couple the protein to the gene expression, it means that every time the cell produces a protein, it also produces this fluorescent protein. They went and observed the fluorescence of each cell, and they observed that actually the levels of protein in a cell are not stable, are not similar between them. Some cells have high levels of expression and other cells have very low levels of expression. Here, the more brilliant the cell, the more amount of protein it has. So these cells that have low intensity of brightness have a lower level of protein, and those cells have higher protein. So this started like a new field about like the study of the variability or random variability of protein levels. We call it noise, as the noise in the sound, because they found like most of this variability is random and cannot be predicted very well. The only thing we can study is the levels, the mean levels, and the stochasticity, and also some trends that we're going to study in this simulation course. Okay, so there are many sources of this randomness. One of them is the cell size. You can see here cells, at least these bacteria, they grow exponentially over time, as you can see here, and they divide. And the time when they divide is kind of random or has some level of random variability. Okay, so here you have some trajectories, and we can estimate here the mean level, that is the darker blue, how the mean change over time. The mean is typical average. And we can also study the noise. The noise usually is measured using the variance, that is the second order moment. We're going to explain it later. Over the mean squared, such as this CV square is a measurement that doesn't have any dimension or any units, it's adimensional. So if you change the scale, you're going to get the same CV square. Also, you can measure the protein number. There are some experiments. Currently, it's kind of difficult to measure actually the number, because you see here what you can see is the level of brightness of the protein. So there are some experiments that currently can measure the protein number, but it's kind of difficult from the experimental perspective. And the number corresponds to the changes as the protein are produced, and the time where the proteins are produced is also random. And every time the cell divides, approximately half of the protein goes to one daughter, and the other half goes to the other daughter cell. And you can also measure the noise. In this case, for the number, usually you use Fano factor. Fano factor is the variance over the mean. So in this case, the Fano factor does have dimensions, but we're going to study it in more detail later. And if you have the protein over the cell size, you have the concentration. And the concentration, you can relate it better to the levels of brightness of this fluorescence. So you can see also you issue the CV square for the protein, and in this case you don't see these oscillations for protein, and also the mean is more steady than the cell size. The idea, like in the future, is like try to simulate these three kind of processes. So we have here like two different ways to model these processes. You have a continuous dynamics, that is the growth, and some jumps. Grow, continuous jump, and growth. And you also have discrete dynamics, as you can see here in protein number. Why? Because the protein number has only integer values, 100, 101, 102, 103. So the dynamics cannot be continuous, as the cell says. And the protein, given that is the ratio between the two of them, is also continuous. So when you have continuous and discrete systems, you have something that is called hybrid systems. hybrid because it's the mix between discrete and continuous. So today I would like to show you how to simulate discrete systems. So we're going to start with the simplest process of a stochastic process is a single step. So essentially you have two possible states. So this state is discrete with two states. It can be, for instance, the production of one protein. So we split our space in two sets, the sets of not having reacted and the set of reaction. So if we start with no molecules, we have the probability of not having the molecule is 1 at time 0. And we want to study how the probability of having reacted evolves over time. We expect like the C probability is going to be 1 when time goes to infinite. And we define here a reaction rate that is a function of, that can be a function of x. X in this case is our number of molecules or our state, can be 0 or 1. So usually what you use here is something called master equation or Kalman-Kolmogorov equation, but we are going to call it master equation. Sorry for master equation. So how to model this master equation? So this describes the probability of my two sets. So it gives us the probability of being in each set as a function of time. Okay, so we're gonna start with a constant reaction rate. As you can see here, we are gonna call it lambda. Lambda approximately gives you how many molecules you perform per unit, you produce per unit of time. Okay. So for instance, if lambda has 10 molecules over minute, it means that you produce on average 10 molecules per minute, and you can use this as a Poisson process, or it's like the simplest Poisson process. Okay, so usually what you do here is for the master equation, you have an efflux that cells, or like the probability is flowing away from P0 and is entering to P1. So the definition of these probabilities is such as P0 plus P1 is equal to 1. Okay, so we're going to use this property very frequently. Okay, so we have we take our flux of probability and multiply it by the probability of being in this state, and it's negative because it's going out. Okay, later with more experience, you're gonna like understand this better. But the idea is this one. And given that this flux of probability is flowing from P0 to P1, the outcoming probability is going, flux is going to the probability of 1. So you have here the same flux, but positive. And you can go and solve this equation, and you obtain these expressions. So this is the probability of not having reacted and the probability of having reacted. Okay, so we can plot this probability of having reacted that corresponds to this plot. And these are like an examples of some trajectories. So all of them start from 0. The state can have 0 or 1. 0 means not having reacted yet. 1 means reaction has occurred. And you have here some trajectories. Examples, and this is the cumulative probability. This is P1 as a function of time. That corresponds to this expression. Okay. We can go. So what is going to be our proportion? Our proportion sometimes is to study the distribution of occurrence times. So for obtaining the distribution, this distribution is called rho in this case. Rho is related to the probability of occurrence or the cumulative probability by this equation. So the integral of the distribution from 0 to any time t gives you the probability. Okay, so you can go to the other side, like solve for rho, taking the derivative on both sides, and you have this expression here, right? So for instance, if you want to study what is the probability of having reacted at time 1, so you take here, this is rho, and you take the integral, the area under this curve, and as a result, you're gonna get this value, no? At time 1, 0.6 something is gonna be the probability of having reacted at time 1. The probability of having reacted at time 2 is 0.8. It means that it means that in this case, 80% of the trajectories occur, or reactions occur, between 0 and 2. If you have this probability, 60 something percent of the reactions occur between 0 and 1. Okay, so we can start like from the simplest simulation technique that is called tau leaping. So what is the idea? The idea is to integrate this system in units of delta t. If somebody of you are familiar with the Euler method, it's kind of the equivalent of the Euler method of integration for stochastic process. What do? We define a time step delta t such as my occurrence rate lambda times delta t is much more less than 1, and we say that the process occur with probability lambda times delta t. So we're going to start with programming a script that simulates the single step process with these two values. Okay, so I already have here my my sitting sheet. Just in case something goes wrong, but I'm gonna start from the beginning. Okay, so here you can go, if you are using Colab, you can go and start from a new notebook, and you can write the same. So the first thing we do is importing some libraries in Python. So we use the code import. One of them is NumPy. NumPy is the library for most of the mathematical functions. Now usually we use as, like we change the name. We use NP. Okay, you go Shift Enter and you import the library. Okay, so here I have I'm gonna use 5 libraries. So the first one is going to be, as I told you, NumPy. The second so far is matplotlib.pyplot. Matplotlib.pyplot as plt. So this library is for plotting. I'm going to use also DQDM that gives you in real time the state of your simulation. We're going to see how this works later. So I use from DQDM, import DQDM, and I won't use this, leave it. And I'm going to use pandas as PD. So pandas is the biggest library of data processing in Python. Okay. So I shift enter and I make a new block using this plus sign here, or use here I can write B. So right clicking here, I write B. Okay. Shift enter. Okay, so the first part is propose these two parameters. So lamp is going to be 1, and dt delta t is going to be 0.0. 0.01. It's okay. So the question is, if the process occurs, so the process occurs with this probability, delta t times lambda. So how do you produce a process that occurs with this probability? So what you do usually is to produce a random number between 0 and 1. You use here NumPy to do it. So NumPy has also a library for random numbers, and you can use the array. Actually it's called random, and rand is a function that gives you a random number between 0 and 1 with uniform distribution, and you use here this parentheses. So every time you call it, you're gonna get a number between 0 and 1. And you generate a process with a given probability if this number is less than your probability. Okay, so you can say, I don't know. So you can assign some probability, let's say 0.1. And if this random number is less than 0.1, the process occurs. So I can use the function print. So here this is an if loop. So if my random number is less than 0.1, I can say I can print the process occurs. Okay, in this case, I ran it and it didn't occur. Didn't. So it has to occur once every 10. I can make this bigger, 90%, and the process occurs. Okay, this probability can be as small or as big as I want, but remember that this has to be between 0 and 1. And usually, like the trick of this simulation is like this delta t has to be y more or less than 0.01. That less than 0.0 less than 1. Sorry. Okay, so the idea is the following: if my random number is less than lambda times dt, I'm going to start from a state equal to 0. And while my state is 0, I increment the time delta t. And if this occurs, my state is going to change to 1. And I'm going to print t. T is the time, right? So I can run this. It is in the script. So if I'm going too fast, let me know. So I run this, and you see, every time I run this, I get a different number. Okay. So in the next cell, I can do this for 1,000 times. So in this case, I make a loop for 10,000 times, and simply copying this and pasting again, and run this in a loop. For cell in. So here I use the function range that gives you like a vector of the desired number of elements, in this case 10. You can see. So give you a vector of 0, 1, 2, 3, 4, 5, 6, 7, and 9, 10 elements. In this case, I'm producing an array of 10,000 elements. Okay, so I can do this iteratively and save the time. And let's see, just printing. No? So here you have different times of occurrence. But I can save this in an array. And instead of printing, I can save it in the array. And I use the function append. Append comes from appendix. That is putting the elements inside the array. Okay, so I'm going to save t. And when I have the t array, I have an array with all the numbers I've simulated. Okay, so here in the code I sent to you, I have this, essentially the same. I simply changed the name of the array and made it for 10,000 numbers. Okay, so I run that block, shift enter. So since it is simulating 10,000 elements, it's going to take a time. And then I can plot an histogram using the function plt. Remember that plt is the matplotlib function. And the function hist. Hist gives you an histogram of my array. So I can see my array here using, here I click here and type A to have a block on top. So this times array is an array of 10,000 elements, each of them being a simulated time of a reaction. Okay, so I plot a histogram. Let's see how it's just this. Just this gives you a basic plot. But I need like that the integral of this distribution gives you 1. So I use density equal to true. And the number of bins. Bins is the number of columns that this histogram has. In this case, I selected 30. And I will compare this with the exponential distribution. Okay. So here I use the function from numpy called linspace that gives you an array of from 0 to 6 of 100 elements. Okay, if I can check it here, dr is an array of 100 elements from 0 to 6, and it has 100 elements. So I can plot using matplotlib.plt.plot tr, and my exponential distribution is lambda times exponential minus lambda times tr. So essentially tr is the array of time. Yeah, and I get something like this. As I expected, exponential. Make sense?
Yes.
Okay. So we can estimate the mean of this time. The mean, remember, is integrating the probability density function, or integrating this function, or taking the average from this function. So for those like to refresh your mind, there's two ways I can estimate the mean. If I have data, the mean of an element or of a data set, that is, I use these brackets, is simply sum all the elements that I and divide by the total number, something like that. Or if I have the distribution from a theoretical perspective, is iterating from 0 to infinite the time times the distribution, or the probability density function as formally it is called. Okay, so in the case that this guy is exponential distribution, we have t times lambda e to the minus lambda t dt. This is going to give you 1 over lambda. Okay. And we can compare this, that is the empirical mean, that is also called the average, with the theoretical mean. Also, you can also check that the variance of the time for an exponential distribution is simply the expected value of the t squared minus the expected value of t to the square. It's going to give you also 1 over lambda. So we can compare it with the simulated trajectories. Usually when you have simulations, or when you perform simulations, you check that everything is fine. If you have simple cases that you can solve analytically. So here I plot the mean. So in this case, it's close to 1. It is not exactly 1, because the number of elements is not high enough, and the variability is relatively high because it's an exponential distribution. But if I run it again, So here I use the function from NumPy min, and I take the mean of times array and I print that function using this function print. And now the mean is closer, but this average or empirical mean is also random variable, so it doesn't have to be exactly one. And when I print, the variance is also close to one. Why? Because my lamp is is exactly one. No? I can make it bigger, let's say 10, and I can run it again. So here you see like the distribution has it's like more less width, yeah, less width, and the mean is 0.10 as we expected is 1 over lambda. 1 over lambda is 1 over 10. That is 0.1. And the variance is also has to be very close to 0.1. In this case, it's 0.0099. Okay, so we have here how to simulate exponential distributed. So here, this lambda doesn't have to be, for instance, always constant. This can be any function of the state and function of time. The advantage of this method is that you can use any rate, and this method always works. Okay, so for instance, here in the script, I had what happens if the rate is lambda times t. Okay, you have an idea what we do here? It's simply I got the same code and I multiply here times t. That's it. Sorry, times t. Okay, so let's see quickly this example. Okay, so now you have an state that jumps from 0 to 1, and the rate is not a constant anymore, but it's a function of time. In this case, it's lambda times t. Okay, so we can also perform our master equation. dp0 over dt is equal to lambda times t minus lambda times dp0, and dp1 over dt is lambda t p1, p0, sorry, p0, because it's the same, but positive. That is the same that as lambda t1 minus p1, because the sum of both probabilities is 1. And I can solve this equation using traditional elements of traditional methods for solving differential equations. It's going to be lambda t times dt. And the solution of this guy, I can integrate this from the side. It's going to be logarithm, natural logarithm minus natural logarithm of 1 minus p1 is equal to lambda t squared over 2. That is the integral of this guy. And I can solve p1 as 1 minus e to the minus lambda t squared over 2. Okay, so it's the thing I have it here. So if I want to study the distribution, it's taking the derivative of this guy. Okay, so sorry for the space. The distribution is the derivative, and the derivative is going to be lambda t e to the minus lambda t squared over 2. Okay, so we can compare our histogram with this distribution. Okay, so run this again for 10,000, and I compare the histogram of my array of time that is here with the distribution that we just obtain numerically, that is, or analytically, that is lamp times t times to the exponential of minus lamp t squared over 2. And you see here the match. Okay, so in this case, your distribution is not exponential anymore, but this bell-shaped function, bell-shaped function that usually is called Weibull distribution. Weibull distribution. Okay, and this Weibull distribution has a parameter, doesn't have to be t, but it can be any power of t. It can be t to the 1.2, and depending on this parameter, you can have different mean, different variability, and so on. Okay, so now you have solved exponential distribution and a success that occurs with a non-homogeneous occurrence rate or non-homogeneous Poisson process. Okay. We keep going. Now we're going to generate trajectories. So what do we need? So I want to produce this kind of trajectories that start from 0 and plot every delta t, and then increase, and then keeps in 1. So you can check the script, and it has this line, but this is later, sorry. So I want to show you, oh no, I don't have trajectories yet. Okay, let's plot the trajectories. Okay, so the same, but we're gonna do the same, but similarly to the previous algorithm, but I'm going to add a line exporting data every delta t, and then plot and save it, and then save it in a data frame and then plot. Okay, so we come here to the previous algorithm. I'm going to copy let's do it under this guy. Let's start with 10 cells. And I'm going to export data every delta t. So now I want, because before I was exporting data every time the event occurs. I'm going to export the state every delta t. So let's use this. I'm going to write an array called data that's going to be empty in the beginning. And for all cells, I'm going to start from state 0 and time equal to 0. So now I define a time maximum, Tmax. So here it is not state 0 anymore, but it's while t is less than Tmax. Okay, so we're going to finish the simulation at time Tmax. Time, I add a delta t, and if the event occurs, the state becomes 1. Otherwise, nothing happens. And I'm going to export the date. So you're going to use data dot append. I'm going to save the number of cell. So let's use here cells and the state of the cell. Okay, and that's it. So I run this, and let's see what do I get. Data is this. So this is the cell 0, and this is the state. It starts from 0, and suddenly it becomes 1. That is the time. It's also missing the time, no? So I'm gonna save the time here. Sorry. Run this again. Data, and you have here the time. But as you see here, there's this problem of rounding. So we're gonna use, instead of t, are gonna export numpy.round. That is a function that rounds your number with a given number of decimal. In this case, we're gonna use 3. 3 decimal digits. And now it makes more sense. 0.01, 0.02, 0.03, and suddenly cell become 1 approximately at time 0103. And the same is gonna happen for cell 1. So we can convert this data into something called data frame using the function pandas. This is like the standard way to use for, or like to deal with data. So we have data pandas is our function PT, and we use data frame, and we use the array to convert it into data frame. Sorry. And we call the columns. So the first column is going to be cell. The second column is going to be state. And the third column is going to be time. Run it, and you see the data frame. Okay, so this way of dealing with data is going to be useful for plotting or for sorting and separate data. Okay, we're going to call it df. Okay, so this data frame structure is going to help you on sorting data and to separate data and so on. So how? For instance, I can say, find me the data such as the time is 0 or 0.01 maybe. Okay. So you have all the states of the cells, cell 0, cell 1, cell 2, cell 3, cell 4, and their particular state at time 0.01. So this cell is in state 1, this cell is state 0, cell in state 1, and so on. Okay. And also I can like select only the cell 1, for instance, df such as, and here inside these brackets or these square brackets, you have the f dot, for instance, cell equal to 5. So this is the cell 5. So you have the state of the cell 5 as a function of time. And you can plot. You can call this data cell and plot data cell dot time and data cell dot state. You have something like this. Okay, start from 0 and then goes to 1. And we can do this for, let's make this smaller, 0.0, because I don't want that level of accuracy, and let's do it for 100 cells. Okay. So this is the cell 5. We save it as a data frame, and we can plot the first 3 cells of the first 10 cells. Okay, I copy this. And paste. And use a lookup for cell in data in df dot cell dot. So this function unique gives you the total cells you have in the data frame. Okay, if I run this, I'm gonna give you the name of the cells 0, 1, 2, 3 until 99. In total, 100 cells. But I don't want to plot all of them, but only plotting the first 10. So for each this, remember that Python inside the for it has to have this index that you can use. You can make it using tab, and the for ends when this indexing changes. Okay, so df cell equal to cell and plot the data cell. So I have something like this. So here the radius is very high. So most of them occurs in the beginning. But I can make this lamp equal to 1 again. And run this, and I have trajectories like this. So for instance, this yellow cell the reaction didn't occur. And these are all of them. Okay, so there's a way to make this like method faster. So this method has the advantage that it works for every rate. So you can put here any function of time, any function of the state, any other function. And it always works, but the main problem is that it takes some time and you cannot have accuracy higher than the delta t. So as you see, you know that the reaction occurs between, let's say, 0.01 and 0.02, but you don't know exactly how, you don't have more more accuracy. So you know exactly the 0.0123, 0.017, etc. So one way to overcome this problem is to use the Gillespie algorithm. So what's the idea? The idea is generating a random number between 0 and 1 and use the cumulative function. Here in this case is 1 minus e to the minus lambda t, cumulative. And when the cumulative is equal to the random number, I get an exponential random number. Okay, so I make this r being equal to t and solve for t. After solving for t, it's going to be 1 minus r logarithm 1 over lambda minus. This is going to be the time of my next reaction. Okay, so in the script I sent to you, you do the same. So for 10,000 cells, you generate a random number with this formula, 1 minus lambda times logarithm of a random number, and we save the time in this array, and plot the histogram, and compare it again with the exponential distribution. Okay, we get something like that. The mean is also 1, and the variance is almost close to 1. And this algorithm is way more faster than the exponential tau leaping. Okay, so in the next block, I do something similar, but plotting trajectories. So the idea is the following. Okay, so first, the thing is like I can from this algorithm, I can produce the times of occurrence very accurate. So if you see here, times array now is continuous. You see you have now times, not only multiples of 0.01, but with arbitrary accuracy. So you have 7, 10 decimal digits. You can go as exact as you want. And but you cannot plot trajectories as you did here with the delta T algorithm. Okay, so what I propose, or like the standard simulation algorithm, is okay. I'm gonna propose acquisition frequency delta T. Doesn't have to be infinitesimal, but it has to be anything I want. And a typical number is if you have a range here, like let's say from 0 to 30, divide this range into 500, and you're gonna get a relative good accuracy. So we estimate the next reaction time using the formula, the Gillespie formula, and the next reaction time. Select the minimum between the next reaction time and the exporting time, and depending on which is the minimum, if the exporting is the minimum, export the data and subtract that time to the next reaction time. And if the reaction is minimum, perform the reaction and subtract the time to the next reaction time. So I'm gonna explain you here like more carefully. Okay, so this is the idea. So for every cell, I start from a state equal to 0. My time is going to be 0, and the reaction time is going to be given by Gillespie. And this time is going to be the exporting time. So I'm going to export data every delta t. So every time t, or while t is less than t maximus, in this case is 30. So I select the minimum of these two guys, the time to reaction and time to exporting. Minimum, and the reaction is going to be the argument of the minimum. So it's going to be 0 if the exporting time is the minimum, or it can be 1 if the reaction time is minimum. And this time I'm going to call it tau, the minimum time. So my time is going to evolve it of some tau, and then if my reaction is 0, I subtract tau from time to reaction, and I save the data. And my new time for reaction is time of exporting is the dt, and if it's the opposite, I do the opposite. Tf, the time for exporting is going to be less tau. My state is going to be 1, and given I don't have more reactions, my time to reaction is going to be infinite because the reaction already occurred. Okay, so I'm going to explain this in another example later, like to explain why this is the algorithm I'm choosing. Okay, so I do the same. You can run from home this code. This takes a little bit. So what's the idea of this guy? So this guy can be exponential in this case, but it can be any other function. So that's why I choose this algorithm. This algorithm is like the standard thing. And you can see here the trajectories. Okay. So I can also say the mean. The mean is like taking all, so let's see. From the data frame I got is something like this. All cells, and for all times I have the state. So I can go and check the data such as the f of time, or the time is equal to a given time, 0.5, and I have all cells and the state at that time. And I can take the mean of this value, of this number. That's the thing I did here. And I save it in the array called MNR, that is the array of mean. And I compare this to the mean of the state that follows this exponential distribution. Okay, so this is the rate. I can do like quickly an example, and showing that this algorithm can work even if the time of reaction is not exponential. Okay, so I can do it quickly. It's just changing, instead of random, we can use any other function. Let's use a gamma function. Gamma function is some bell shape distributed. So it has some shape. It's only for showing you, no? It's not for. That's it. So now the distribution is going to be something different, but the times are not exponential. And the mean is going to be something different. Okay, so this idea, or this kind of process or algorithm, is going to be the basis of all the simulations. So that's why it takes this much time. Okay, this has to be. Sorry, I didn't save this as data frame. So now this is the mean. So it's going to be something different, okay? But this algorithm works for any other distribution. Okay, so before ending, I wanted like to do more, but let's see quickly this, and we'll finish in the next session for this telegraphic and Poisson. Okay, so this is the second file I sent to you. So sorry, delete this. So what's the idea? The idea of this is now you have two-state system, but you can come back 0 and 1. But there's also there's a transition rate lambda from 0 to 1, but there's also transition rate from 1 to 0. Okay, so the master equation now is something similar. So now I have the state 1 and the state -1. Well, sorry, it can be 0, but put the name that you want. No, doesn't have to be -1. So the idea is like this. So from this, you have an efflux from 0 to 1. So you have a negative number here with rate lambda. And the same from 1 to 0 with rate lambda. So it's incoming. So the flux is positive. And you have the same for P1. So you have an influx from 0. So you have lambda times P0 minus lambda P1, that is the efflux. Okay. So you can propose this equation, this master equation. So one example of these reactions can be around the environment, that you can alternate the environment between nutrient or scarce nutrients, or for instance, hot and cold, or other cases can be the phenotype of one cell that can be persistent or non-persistent to antibiotics. Also, the phage lambda can select that is a virus that attacks bacteria, can decide between being harmful or just neutral with bacteria. Also, you have other system metastable systems such as GAL for yeast taking galactose, or LAC for bacteria metabolizing lactose. Okay, so from the master equation, you can put it in matrix form. You start from state 1, 0, apply this exponential matrix, so this is the solution of this master equation, and you get something like this. You can go and check in Wolfram. And from these, you can obtain that the probability of being in 0, or the lower state, is 1 minus plus exponential of this, and the probability of being in 1 is 1 minus exponential over 2. Okay, so the steady state of this guy, I mean, the limit of t going to infinite is 1 over 2, and the probability of being in a state 0 or -1 in this case is 1 over 2 as well. Is that limit t going to infinite? No? And from this, you can estimate the mean, that is taking each value times the probability. So -1 with probability of -1, and 1 probability of 1. This is 1. So you have that the mean follows this equation, and the variance follows this other equation, the same. Okay. It depends on how do you define your states. Okay, so how do we simulate this? The telegraphic way is going to be something similar. So we have again 2 times: the time of next reaction, and that we use Gillespie formula, and the time to next exporting, or the next time to export date. Okay, so what happens if the state of exporting data, that is here in vertical line, is less, we are in 0, no? It's less than the time to next reaction. So next reaction is going to occur here at time 0.7 approximately. This is reaction. And the next time for this, this is exporting date. So here this time to reaction is going to be Gillespie, no? 1 over lambda logarithm of R. And this time to export is going to be delta t, let's say 0.01 or whatever. So you pick the minimum. In this case, the minimum is this, the experiment. So in this case, do nothing and export data. But if the exporting data is greater than the reaction time, you first do the reaction, and then the new time for exporting is going to be this time, no? So let's do with different color. How can I change the color? Here, this time next exporting in red, and next time to reaction. Any question? Reaction, export.
Thank you. El sistema fotovoltaico
And
sí,
esa es. Ya está un avance. Está un poco muy.
so the next time to reaction, you perform the reaction, and the next time to reaction is going to be this. So you subtract from the previous time to reaction this time. Okay, this is going to be. Okay, this is still. Okay. This is the idea. Okay. That's the thing I did. So again, so I have time to reaction, time to export. I took the mean, and depending on the reaction, I get, if it's 0, I subtract to find the reaction, I subtract the time to export. And if the minimum is time to export, I subtract the time to reaction. So in this case, I did. In this case, time to reaction was this, sorry, time to export was this, and time to reaction was this. So in this case, I subtract the time to reaction. So the next time to reaction is going to be simply this small. That's the thing I'm doing. And given that there's no reaction anymore, I have well, this is for one step, but now I do the opposite. So if the first reaction is exporting, I subtract the time to reaction, the exporting time, that's the minimum, and save the data, and new time for reaction is going to be delta t again. Otherwise, the time for exporting, I subtract the time to reaction, and if it's the state is 0, jumps to 1 and get a new time for reaction every time. Essentially it's the same. So you have something like this. Okay, it's a typical trajectory. I can do this for 1,000 cells, and I save it in a data frame. Similarly, I have to import this. So you can check it more carefully from your places and can ask me questions for the next session. Here I use this library TQDM that gives you the current time of your simulation. So for using it, instead of using the 4, I use TQDM in a parenthesis range. And that's it. And this gives you how much time you need to finish. What do I do? Let's wait. So I'm going to save this in a data frame from this data. So I have cell, time, state, and the same. I'm going to calculate the mean and the variance, and save it as in a new data frame. It's going to be data. Let's call it data 2 because it has the same name of this. So we finish when in 10 minutes or no?
I think we finished now.
Okay. So let's finish here with this, and we discuss next session. So here is my expected mean time. Maybe 30 seconds. That's it. So for the next sessions, maybe I wanted to show you Poisson process is essentially the same, but instead of switching here the state is just adding a new element, s equal s plus 1, and you have the same. You can go and check from your places. Maybe we can discuss next Thursday. But overall, all the simulations are going to have the same structure. So hopefully we should apply. You can go from your places and check what's the rest of what does the rest of the code do. You get something like that. Okay, so thank you so much. Any question we can discuss in the next session.
Thank you.
Okay.
Thank you.
Mhm.
Thank you.